Reducing to a more general case, vertex cover to set cover. Independent set and vertex cover represent two different genres of problems. Independent set can be viewed as a packing problem. The goal is to pack in as many vertices as possible, subjected to conflicts, the agencies that try to prevent one from doing this. Vertex cover, on the other hand, can be viewed as a covering problem. The goal is to parsimoniously cover all the agencies in the graph using as few vertices as possible. Vertex cover is a covering problem phrased specifically in the language of graphs. There is a more general covering problem, set cover, in which you seek to cover an arbitrary set of objects using a collection of smaller sets. We can phrase set cover as follows. Given a set U of n elements, a collection S1, S2, S3 until Sm of subsets of U, and a number k, does there exist a collection of at most k of these sets whose union is equal to O of U? Imagine, for example, that we have m available pieces of software and a set U of n capabilities that we would like our system to have. The ith piece of software includes the set Si, which is a subset equals to U of capabilities. In the set cover problem, we seek to include a small number of these pieces of software on our system, with the property that our system will then have all n capabilities. Intuitively, it feels like vertex cover is a special case of set cover. In the later case, we are trying to cover an arbitrary set using arbitrary subsets, while in the former case, we are specifically trying to cover agencies of a graph using set of agencies incident to vertices. In fact, we can show the following reduction. 8.6. Vertex cover is polynomial time reducible to set cover. Proof. Suppose we have access a black box that can solve set cover and consider an arbitrary instance of vertex cover specified by a graph G equals to VE and a number K. How can we use such a black box to help us? Our goal is to cover the agencies in E, so we formulate an instance of set cover in which the ground set U is equal to E. Each time we pick a vertex in the vertex cover problem, we cover all the agencies incident to it. Thus, for each vertex I in V, we add a set Si, which is subset equals to U, to our set cover instance, consisting of all the agencies in G incident to I. We now claim that U can be covered with at most k of the sets S1, S2, S3 until Sn, if and only if G has a vertex cover of size at most k. This can be proved very easily if Si1, Si2, Si3, and so on until Sil or L, which is less than equals to k sets, which means that there are L sets that cover U. Then every H in G is incident to one of the vertices I1, I2, I3 until IL, and so the set I1, I2, I3 until IL is a vertex cover in G of size L, which is less than or equals to K. Conversely, if the set I1, I2, I3 until IL is a vertex cover in G of size L, which is less than or equals to K, then the sets SIL, SIL minus 1, SIL minus 2, and so on until SI1 cover U. Thus, given our instance of a vertex cover, we formulate the instance of a set cover described above and pass it to our black box. We answer yes if and only if the black box answers yes. You can check that the instance of set cover pictured in figure 8.2 is actually the one you'd get by following the reduction proof. Here is something worth noticing, both about this proof and about the previous reductions in 8.4 and 8.5. Although the definition of The polynomial time reduction allows us to issue many calls to our black box. For set cover, we issued only one. Indeed, our algorithm for vertex cover consisted simply of encoding the problem as a single instance of set cover and then using the answer to this instance as our overall answer. This will be true of essentially all the reductions that we consider. They will consist of establishing y, which is a polynomial time reducible to x, by transforming our instance of y to a single instance of x, invoking our black box for x on this instance, and reporting the box answer as our answer for the instance of y. Just as set cover is a natural generalization of vertex cover, there is a natural generalization of independent set as a packing problem for arbitrary sets. Specifically, we define the set packing problem as follows. Given a set U of n elements, a collection S1, S2, S3 until Sm of subsets of U and a number k, does there exist a collection of at least k of these sets with the property that no two of them intersect? In other words, we wish to pack a larger number of sets together with the constraint that no two of them are overlapping. As an example of where this type of issue might arise, imagine that we have a set U of n non-shareable resources and a set of m software processes. The ith process requires the set Si, which is a subset equals to U of resources in order to run. Then the set packing problem seeks a large collection of these processes that can be run simultaneously, with the property that none of their resource requirements overlap, i.e. represent a conflict. There is a natural analog to 8.6, and its proof is almost the same as well. We will leave the details as an exercise. 8.7 independent set is polynomial time reducible to set packing.